So let's continue on seeing more theory on Planck's constant. So we'll continue. That first point would be the energy released or absorbed in the form of small packets of h nu, 2 h nu, 3 h nu, and so on up to n h nu. So this n can't be in fraction. Okay. Energy released or absorbed in the form of small packets of h nu, 2 h nu, 3 h nu. This would be the energy of quantum rather, and from now on these all would be quantums or quanta rather. 3 h nu, 4 h nu, 5 h nu up to n h nu. Okay, these all will be quanta. Okay, so this n can't be in fraction. Okay, next let's see about the, we know that speed of light, I'm denoting it by c, is frequency into lambda, which is frequency into wavelength. Next we can derive that frequency would be nothing but speed of light divided by frequency of light. So just putting this value in E equals to h nu, we will get E equals to hc by lambda. Okay, so from here we can derive that energy is directly proportional to Planck's constant, and energy is inversely proportional to lambda, okay, or the wavelength. So let's do some quick questions on it. So FM radio station broadcasts electromagnetic radiations at a frequency of 1240 kilohertz. What is the wavelength of radio waves? Wavelength of radio waves. Okay, so we know that lambda is c upon frequency. So c is obviously 3 into 10 raised to power 8. Frequency is 1240 second inverse. Sorry, it's kilohertz. So 1240 into 10 raised to power 4 second inverse. Okay, so from here you can calculate the required answer. And next we have here, what is the ratio between energies of two radiations? Ratio between energies of two radiations, one with a wavelength of 600 angstrom and another with a wavelength of 2000 angstrom. Okay, so we know that energy is inversely proportional to 1 upon lambda, as we know that energy equals to hc by lambda. Okay, so E1 would be hc by lambda 1, and E2 would be hc2 by lambda 2, or rather E2 is equal to hc by lambda 2. Okay, not c2. So ratio between E1 and E2 would be ratio between lambda 2 and lambda 1. Lambda 2 is 2000 angstrom, lambda 2 is 6000 angstrom. Oops, there is some problem here. Yeah, So the ratio would be 1:3. Okay. Now the next question is, find the number of quantum radiations of frequency as 10 raised to power 13 second inverse that must be observed in order to melt 6.626 grams of ice. Okay. The energy required to melt 2 gram of ice, and you have been given the energy required to melt 2 gram of ice is 666 joules. Okay. So first let's apply the unitary method, that for 2 grams you require 666 joules of energy, and for melting 2.626 grams of energy, 626 not, we would be requiring 0.2 multiplied by 6.626 joules. Okay. Hence you have been asked to find the number of quantum radiations required. Okay. So number of quantum radiations required would be, you can find it easily with the formula that you have been asked to find nh nu, which should be equal to this much amount of energy, rather 626. Okay, so n would be 666 into 6.626 upon 2 into h would be, again, what would be the value of h? H would be again 6.6 into 10 raised to power minus 34 joule second inverse, and joule second, and nu would be, or frequency would be 10 raised to power 13 second inverse. So using this, so this is rather 6.26 only the h value, so you can easily calculate the number of packets or number of quantums of radiations required. So do the math and find out the number of packets required. Okay. So next let's discuss a problem wherein you have to calculate the number of quantum having, you have to calculate n having lambda as 100 nanometer, which can provide energy of 1 kilojoule. So n would be E upon hc into lambda. Okay. So 1 kilojoule would be nothing but 10 raised to power 3 joules. Lambda is 100 into 10 raised to power minus 9. Okay, and h would be 6.626 into 10 raised to power minus 34, and c would be 3 into 10 raised to power 8. Okay, so you can calculate from this values what would be the number of n required. Okay, so with this we come to an end of this lecture. In the next lecture we'll be seeing photoelectric effect.